Okay, good evening, everyone. Sorry, we're a little bit late starting. We had trouble with the audio of the lovely new room and the setup. So my name is Stephen Pereira. I work here at Just Eat, so thanks to Just Eat for sponsoring. We have some lovely talks tonight. A talk again on Loki, serverless platform for data at AWS, very interesting. And again, Kubernetes platforms and a real world journey. So, will it work? Always fun. Give me 1 second. Move. Eunice, I blame you. You have too many tabs. Like, there's like a million tabs. What are you looking for? I'm looking for the slides so I can back over. I just added them back. Where are they? There they are. Yeah, there you go. Okay.
Is the actual Zoom?
The Zoom is on, and I did manage to turn the mic on before starting. So there you go.
So okay.
Yeah, that's for this to me.
Okay.
Okay. All right. Let's try that again. Welcome to Cloud Native London. We have talks tonight. Hashtag Cloud Native London, as always. And a strong, open, diverse developer community dedicated to cloud native platform and technologies in London. It's me, Stephen Pereira, here at Just Eat. Just standing in for Cheryl. She will be back very soon. So we, okay. We're already going over this. And so thanks to the sponsors, to Sysdig, Screenly, and us here at Just Eat. We have some problems with the room audio. So my audio is actually going out directly from this laptop, which is why you can't hear me. And I'll try and speak up. And I'm sure all of the presenters will do as well. We should have all this cleared up by next month. These rooms were just built and we didn't have a lot of time to test the audio. I'm sorry. Okay. Are you here? Then please do come up and say what.
Hey, Victor from Screenly. This is my first meetup since COVID times. This feels weird. It's a long time. So I'm Victor with Screenly. We do essentially screen operating systems. So think of things that drive vending machines, checkout counters, dashboards, anything in between. If you are looking for a gig, we are hiring. So we are looking for a DevOps guy that is passionate about zero trust, security, scaling. So if that's something up your alley, do let me know. Me and Althea, right there in purple, will be around for the rest of the evening. So let us know. We also hire for a senior device developer. If somebody's kind of out of the DevOps space, we're also hiring for that. But essentially, if you want to work on really cool cloud native stuff, we are super interested in talking to you. So hit me up after the talks and looking forward to learn more about you. Thanks so much. Cheers.
Okay. I will plug Sysdig. I like it very much. It's a very nice tool set to use. Okay, seeing as we're running a little bit late, Kubernetes Community Days UK. I guess everyone take a picture of that QR code if you want to go.
Yeah, messages afterwards as well.
In the messages afterwards as well. Thank you. I'll leave that up there for anyone who wants to take a snap. Big 25% discount. Okay. All right, no one taking pictures anymore. All right. Okay, so to the questions from tonight. Is this your first time at Cloud Native London? Poll still on the top there. Yeah, it is. The poll might even work this time. We don't. 50-50. Oh, it's going down rapidly. Okay. We definitely need to put the number of respondents up on the poll. Oh, that's pretty cool. All right. So for everyone new to Cloud Native, we are normally better organized than this. Very nice. Okay, and what is your job title? Architects, oh, as SRE. No one here from security. Other. Pretty even split.
They hate yellow paint.
Do they? You would have thought that they would be trying to make it a better and safer place for us all. There we go. So really even spread. Awesome. Going. Which logging solution do you use? Lots of Elasticsearch, some Splunk, something else. Okay, that I didn't expect. Our percentage for Elasticsearch is going down. Very interesting. Splunk being acquired recently also. What is the name of the AWS service that builds serverless Apache Spark jobs? Well, if we were doing Who Wants to Be a Millionaire and we were asking the audience, we might have a problem. Okay, how many Kubernetes clusters do you have in your environment? Ten. Wow, we have some people with 200 plus clusters. So 200 sets of masters. Okay, and we keep going. What is your most challenging topic in Kubernetes? Questions that are not unrelated. Security and compliance and multi-tenancy, cluster sharing. Looks about right to me. They're more overhead to run than people think. Oh, selfies. I've been practicing my selfie technique just at this moment. We can't do it now. We're only split in half. We need like two. And do we have the first speaker? We have more speaking slots available from 2024. Just go to the website and register. Nobody has responded. Should we skip the questions? Yes, let's do it afterwards. Okay. Do you want to? I will stop sharing.
Second, I need to set up laptop.
Yes. Again, apologies. Right. Stop. Cool. You go for it. I will get out of the way.
Sorry, what was the code again? Because I think I lost my.
Was it the how you got connected?
No, not
Rejoining
anymore.
now. Okay. DTM.
That one.
DTM. JHNE. IOG.
IOG, yeah. Sir, I'm gonna have to put in my earphones for people on Zoom to hear me. Sorry about that. Hey, thank you. Welcome, everybody. I'm not any of these people. I just took an existing presentation because the solutions engineers and salespeople are a lot better at doing presentations than me. I'm Michel Hollands. I'm an engineer from the Loki team at Grafana Labs. I'm sure a lot of you know Grafana, but might not know where Loki is exactly in the stack. So Grafana is the tool that you use to visualize dashboards and graphs. And Loki is actually a fairly big part of Grafana Labs. Is we have solutions for storing metrics, logs, and traces. They're called Mimir, Loki, and Tempo. In addition to that, we have a bunch of other products like for on-call, for load testing, but I'll only be talking about Loki today, basically. So I'm sure a lot of you know the 3 pillars of observability. There's actually 4 of them now. We've got profiling as well, but these slides haven't been updated. And the way that these 3 are connected, and the 3 pillars are metrics, logs, and traces, and they are connected in various ways. And today we'll mostly be talking about the metrics to logs and the other way around. That's good. And the gist of it, the thing you have to take back is that with Loki, you can basically take whatever you got for your Prometheus or your Mimir. If you have a in there, like you have a Mimir query, you can just take the label part, put that in Loki, and you should get the logs for the same time for the same service. Basically. So why Loki? Yeah, Loki was built by our current CTO, Tom Wilkie, started in 2018. I don't think he had anything to do with this this tweet or this X or whatever you call it now. So, but that's basically the gist of it. So he wanted to build like a grep that will run over multiple log lines in parallel instead of having to index everything beforehand. So then basically Loki is built. You could look at it a bit as Prometheus, but for logs. And it's mostly used at the moment by developers and operators, although we are seeing people using it for like general search as well. The sort of the goals for building Loki was, first of all, it has to be economical to run. So we don't want to store too much data. We want to store it in a nice way. I'll get to that later on. Should be fairly easy to operate. And then the integration with Prometheus was really, Tom was working actually on a product called Cortex, which is now Mimir, which is a Prometheus at scale. So Loki was like a natural evolution from there onwards, basically. So this is more maybe a sales people like slide. At the moment, people have a lot of different systems, and we at Grafana Lab really love it if you use Grafana Lab all the way around. That's for the salespeople. So what Loki is used for mostly at the moment is debugging production issues. So people will send all their logs to us. They will have alerts and metrics and dashboards, and the alerts will fire. And at that point, when you wake up at 2 in the morning, you have to find out what was happening in that server when this alert went off. You can look at the metrics. If you don't find anything there, you can then easily switch to the logs and see if there's any messages there, anything that went wrong, anything that isn't captured by metrics. And then move on to traces as well if there's a timing issue or something like that, or a certain service is taking too much time. So Loki is really built for that debugging and troubleshooting applications, basically getting up and running again. And then also what you can do, and I'll show you some examples of that, is basically build alerts and graphs and dashboards based on log files, basically, purely on log files. And at the end, I'll show you a good example of that. It's starting to get used as well with a few other cases. A lot of the cybersecurity people like it because it's actually, they can log a lot of data and then process that data later on, because usually they need to find out what happened at a certain point and then go back and find out how did we get there. And that's because with Loki, you don't really have to restrict what you log. It's fairly cost effective. You can just log everything and then filter it out later on. Okay. So the way you get logs into Loki is actually very easy. It's pretty much anything you can do. We don't have any restrictions on what you log, except maybe binary data. There's no point in storing binary data, right? See, there's no way to query that, but any log format will work. Anything can go. The full API is basically just a normal HTTP API. So it's very easy to point clients to this API. And as we can see, there's all of the logging agents that exists. Pretty much every one of them, they support Loki. These two are the ones from Grafana ourselves, so Prometheus. Then Prometheus is specifically for logs, sort of historically the agent you would use for logging and for sending logs to Loki. Grafana agent is sort of a roll-up, so that does both logging, metrics, traces, profiles, and it's basically, it can do everything that Prometheus does as well, in addition to those other things. So how do we store logs? And this is a slide that will come back again, I'm afraid, but this is basically the gist of it. We don't index the logs. We just index where your logs came from. So the labels that are attached to your logs or added to your logs by your agent, we only index those ones, and then we use brute force to search through the rest. I'll give more examples of that. This is sort of the trade-off. Again, this is maybe more marketing side. It's against Elasticsearch or OpenSearch or whatever you want to use. But basically, the biggest thing to remember is that we you don't have to set up your indexing beforehand with Loki. You basically store everything. And if you want to extract, if you want to filter on extra fields that you haven't thought of before, you can do that at runtime. I'll give more examples of that. And that means that you don't have to do a lot of processing beforehand. So you don't have to store anything in an index. You can do very fast writes because of that as well. And maybe the one thing that the trade-off you have to make there is that if you're looking for something very specific, then Elasticsearch could be better because they index everything. They use a lot more storage space. So that's the sort of the trade-off you have to do, basically. This is the way it works. So basically, the only things that are indexed is the timestamp, and then a group of labels, which we call a label set, and that comes from Prometheus, this terminology. So there's a group of labels that uniquely identify where this log line came from. So that's so the actual content is not indexed. That's just stored one after another in chunks on object storage. The way you would search this then is basically usually you specify a period where you want to search your logs. You then specify your log selector, which will select one or more sets of labels, basically. So in this case, it will select for the label app, it will select Nginx. And for instance, it uses some sort of a regular expression there. So any label that has a value starting with 1 will match here. And then you can, all the lines you get back, you can then filter and then transform. So in this case, we only filter the ones that have error, and we remove the ones that have bad icon. So that's not needed. The architecture of Loki is actually fairly similar to a lot of like Mimir and Tempo or other products. And there's a few bigger open source products that use a similar architecture. It's basically where the write path is separate from the read path. So basically in the write path, first your log lines come in through a distributor, which will shard your log lines, your labels basically, and send labels for the same label, send them to specific ingesters. So that, how shall I say, the same ingester will receive log lines for the same label set that you have. The idea is there that we can then, in this ingester, keep a list of all those log lines for one, put them in a big chunk, and then store that chunks after a while. By default, it's like after 2 hours or if a certain size is reached. This ingester can also be used for querying. So if you need to know your most recent data, you can get that from there. The query will actually do that for you. On the read part, first, when a query comes in, it's split up into multiple sub-queries almost, in a sense, by a thing called the query frontend. That's just for performance. We want to do, a grep over parallel grep over a lot of data. So we want to split that up into a lot of sub-queries going on at the same time. And it's then the queryers, where you have loads of them, they will run that query over the actual object storage. One thing I should mention here as well is that we only use object storage. So we don't have a database for the indexes. That's purely done. Everything is only done in object storage. So that helps with the cost, because object storage is actually very cheap compared to everything else. And the nice thing is that if you use something like S3 or the Google or Azure equivalents, they're very, how shall I say, like durable and performant. And the nice thing is they scale as well. Although we didn't manage to overwhelm them occasionally, which was quite nice as an engineer. Next, and then like I said, everything is stored on object storage. So that includes the indexes and the actual log lines. We also have a compactor component that will, one thing I forgot to mention is that when the distributor sends the data to an ingester, it will send it to multiple ones. This is just for fault tolerance, just in case one of your ingesters falls over. You're in Kubernetes, right? The node could go down. So we always have multiple copies going on there, and they all write those multiple copies to object storage. That also means that you have multiple indexes for the same data. And we have component called the compactor that sort of cleans things up there. So you only have one index, which speeds up, well, querying basically. Additionally, we also have a ruler, and this is very similar to the Prometheus ruler, if people know that one. So that's basically a component that will run a certain query at a certain time, check, generate some result there, and depending on what you're doing, it will either create a new metric or it will create an alert. I'll show that next. And then the alert manager, that's technically not part of Loki itself, but that's just the standard Grafana or the Prometheus alert manager. Sorry, so I say Grafana because we employ most of the people working on the Prometheus team. So for the parallel querying, there are some numbers that we've actually seen in production. So if, let's say, a customer has a petabyte of raw logs, after you, in your query, you select some labels, like cluster or job here, that will whittle it down to about 80 terabytes, for example. You then have a certain time frame, the last hour or whenever your incident happens, that will then whittle it down again to 1 terabyte of data you have to consider. And then what we then do is that we take that query, we first split it up by time. So you get 15 minutes of 50-minute chunks. And then for each of those time periods, we will run multiple queries in parallel. Each querier has what they call workers. So in this case, there's 4 workers, and they will then search in parallel, return the results to your query front end who combines everything and then gets the query back. So we've seen over, this number is actually a bit old, but see more than 60 gigabytes a second. We've actually seen a lot more recently. The way you get logs into Loki is through Prometheus or the Grafana agent. These agents actually don't have to do too much. Basically what they do is they watch for your environment to see where they should get the logs from. This is very similar to Prometheus, if people know that one. In Prometheus, you can say, give me all the Kubernetes pods that have these label and this value. And whenever there's a new one that comes up, just start monitoring that one as well. Prometheus and the Grafana agent have the same functionality there. They attach a few labels, but not too much. So they basically don't process the full log line if you don't want to. You can if you want to. There are steps where you can sort of add some regex filtering, or if you want to, personally identifiable information. If you want to remove that one, you can do that, but you don't have to. So most of the time, these agents will basically just take the log line and push it actually to the Loki instance straight away. Alerting, if people have seen Prometheus alerting, Loki alerting is actually fairly similar. So the expression you see here, expression cluster job rate namespace, what this does is that it looks in your logs, checks if the rate of the occurrences of a line where you have HTTP, let's say a user : password @ if that is more than 0, then you raise an alert basically. So that's whenever somebody has used a direct HTTP basic auth credential in their query, you want to raise an alert because that's something that gives away your login details basically, right? You want to avoid that one. So that's what you could use these Loki queries for example. Similarly, recording rules are also very similar to what you have in Prometheus, but that's basically a way to summarize data. That instead of having to, but basically you run a query that summarizes your data down to one line, and you run that at a periodic interval, and then later on you can use that summarized data to run your queries a lot quicker. For example, here it's getting the response statuses from an HTTP log, or for the ingress container, counting them over time and then summing them by the code, by the HTTP status code. If you then later on want to get all the counts for all the status codes, 200s for an hour, you don't have to process all those lines anymore. You only have to process those lines, those 10 seconds, that one line for every 10 seconds. So that's a lot less data. Sorry, this is the one I mentioned I was going to come back. This is really our the main new thing in Loki, basically. That bears repeating. So the difference is, if you looked at, for example, at Elasticsearch would create a record for every field you define, whereas on Loki we would only have indexed records for the timestamps and then the labels you've got here. So instance and job, those would be the labels. If you know Prometheus metrics, which I should have asked before, this is sort of the database, the data model that Prometheus uses. So you've got a timestamp, a metric name, labels, and then a value. And like I've shown before, the Loki one is it's pretty much the same as what you have there. In fact, even in our first version of Loki, we in between there the timestamp and the Prometheus label, we actually had a metric called logs, which was hard coded for everything. So we're wasting so much space just putting a hard coded metric there. Like I mentioned before, you try and send everything to the same ingester, and that is done through a thing called streams. And a stream is basically like a list of logs with the same labels. So in this case, the first 3 are in the same stream, and the second 2 are also in the same stream. What you do have to do when you use Loki is you have to select good labels, and that's usually one thing where we do have we occasionally have to help customers there get the right ones, because what you want is, for your labels, you want them to be not too high a cardinality, and you also want them to be like fairly stable as well over time. So good ones would be like cluster, namespace, job. Those are going to stay roughly the same, right, most of the time. Whereas something like trace ID is basically just a random number. You don't want to index that because it's not going to show up anymore. So you don't want to create like a separate stream and a separate file on disk just for that trace ID. For querying, by the way, the language used to query Loki is called LogQL. So what you usually do in a query in LogQL is that you first you specify your label matchers. These are the ones we've seen before. So where you match one or more labels, that then returns a whole list of log lines, and then you filter those out using filter expressions. Here in this case, we select the trace ID, and we do a regex expression on series store. So any word that starts with series, or if your line contains a word that starts with series store, it will be matched. This is just sort of very simple, normal filtering, and anybody can do that. Another thing we do as well is creating labels at runtime. And for that, let me show you this example here. This is just like some HTTP access log. What you want to do is you want to, for the HTTP verb, basically, or the HTTP command that you see here, you want to extract the path, the status, and then also the size field here, which is the one after the blue one. And for some reason or another, this query wants to get the maximum, which I don't know why, but that's what I wanted to do. The way you do that in Loki is basically that you have your query. So app equals nginx. Here you just get the streams for this one label set. And then you can say, run this regex for every single line. And which parts of the regex match, create new labels based on the what's in the P field here. So you're going to have a new label called path, status code, and value for each of those. And then you can run your query. So you can just sum over the path and the status code and return the value for each of those, the maximum over time for that value. This is sort of a quick summary, actually, of all the commands you can do in Loki. We have multiple parsers. So we've just seen the regular expression one. Another one is log format, which is the one we actually use ourselves. That's basically just key equals value. And then the key will be the name of the label. The value will be the value of the label. JSON is basically just you get a JSON blob, which you turn into labels. That can be nested as well. So they will just have a dot in between for the key name. And then there's this very simple one, pattern, which is just any space separated fields. So what you can say there is, I have a line that contains 5 fields. I want the third one and the fourth one to be named, diameter and longitude, for some reason or another. And those will then become labels, and everything else will just be ignored. Then for filtering, we've already seen where you can do equality search. You can search the full line, which is with the bar equals. You can also have some sort of condition against the labels. So if you create a new label, that label will be available for you in that same line. For example, if you've extracted a label called foo, you can say now foo bigger than 10. Only select the lines that have this value bigger than that. It also understands like so some durations. Basically, Loki is written in Go, so any of the Go any durations that Go can parse by default. So those can also work. So here, for example, you can do anything bigger than 23 milliseconds. You can also rewrite what you return. I'll show an example for that because that makes most sense there. And then we have a whole bunch of functions for showing graphs. Okay. And here's sort of the demo part. So basically, these are the log lines. This is the Loki API, the Loki UI, basically in Grafana. So here we're just selecting all the log lines from that have a label called file name with this value, JSON access. And they look like this. As you can see, it's a JSON blob. Got fields like status, body byte sent, GeoIP country code. And now this dashboard here, for example, this is a demo dashboard that's only built using Loki, only using Loki queries. So let's start with a simple one. The number of log lines. Basically what this does is this counts over time how many lines you return, and the interval is going to be set to the field you set here, basically the last 6 hours. That's what that interval variable means. That's a Grafana specific thing, actually. And the way we're filtering out here is that we're basically just using existing new fields in Grafana, like the fields on top there, label, value, and job, and instance. And those have if you have an all value there, that just means that they match everything. They're basically a regular expression called dot star. So basically what this query does is just select anything from the JSON access log. We don't care about the job, we don't care about the instance. And then just count them over time over the period that you've selected. And then that will show you how many log lines you got back. More interesting one is this one here. So this is a geo panel. So what we do there is you basically select those same lines, but we don't parse them as JSON. And if they have a field called GeoIP country ID and it's not empty, then we select the line. We also have an error statement there, checking for errors. That's just if there's an invalid JSON in there, that you can filter those out. And then we sum that by GeoIP by country ID. And this can then be used as input, like here, for example. So in this case, the return value would have been ML with a value of 2. And that's just the format you need as input for a geo panel. Similarly, you can also do a top K kind of query. So you get the top 10 in this case for the interval of the geo country codes. So these are the ones that have been sending the most requests in this case. And lastly, you can filter the output. Get Slack out of the way. Okay. So what we do here is we've got the same query. We parse it as JSON as well, but then we use the line format command. So that basically takes changes the output. What it does here is it prints this right arrow, and then the request method is the JSON field request method that was generated by the JSON parser, and similarly for the URI and the status. then your output looks like here, where you have these the line get and the request with the HTTP status, basically. This is used a lot for. You can also run. There's a command line client for Loki, so it's quite useful to generate reports in that case. All right, and that was basically it. So, come on, time. Okay. Thank you very much. I don't know how we do questions here, though. So, if you have any questions, where are they? I'm sorry, this is the first time I'm in this meetup, so I don't know how things usually go here. But if you have any questions, I'll be around. Come and ask me, or. Sorry, the path parameter. Was this on one of the slides or on? Okay, well, let me go back to the slides then. Is it this one here? Yeah, well, basically what happens here is that you see this regex, right? So app equals nginx, everything that's before the regex is just selecting the lines. And then for every line, the regex gets applied, and anything that matches, and it matches over the whole anywhere in the field, basically, anywhere in the line, basically. So if there's something that starts with get, and then you have this the path part here. This is like a feature of regexes where you can give a name to something that matched. So in this case, the brackets make it like this is a new field that you're going to return. The dot star just means anything. You know, it matches everything. So anything that comes after get, and then is a continuous list of characters without a space, basically. That then becomes the field part or the label part, temporary label. It's just for every line that gets created. And similarly, like the HTTP part here, that's just the text it has to match as is. And then there's another field, which is 3 decimal numbers, basically. And we call that one status code. And then similarly for the value one, that's just a number. Does that make sense? Yeah. It's but we like we said, Loki is written in Go, so we use the Go regular expression syntax there, which works with this. Anybody else? Yeah. Okay. So the question was, what's the argument for not using Loki? And it's like sort of the needle in a haystack search, like which we see, and we in Grafana Cloud we have that as well, actually. So luckily, because we run a lot of parallel queries, we can sort of mitigate that a bit. But that's definitely an expensive one for now. We are looking at ways of working with that, but actually, if I can make any, if I can advertise a little bit, we've got OpsCon, Grafana OpsCon coming up in November, so you might want to look there. Hint. Cool. Anybody else? Okay, that's it then. Thank you all for listening, and I'll be around if you have any questions.
So my speaker should be on for the Zoom, right? Where should I share my screen again? Okay. Does it work?
If you
Yeah.
joined that by the
Yeah. The companion
so you
mode,
share-
and then to share the screen, right?
Yeah, exactly.
So sharing an audio is in Zoom, right?
Yeah. Share in Zoom and then share on Meet.
Meets too as well. Okay.
Otherwise, the room won't see it. But
Yes,
it will
yes,
still
yes,
be
yes,
online.
yes. Cool.
Okay.
So we have the screen, we have the Zoom. Yes. And yes, it seems we're ready to go. Right? Okay. Let me know if I speak a bit too quiet. But hi everyone. We're going to talk about building self-service serverless data platform at Amazon and how we used it to scale our platform to support hundreds of data sets produced by tens of other teams. So the agenda of the talk would be, first, I'm going to talk about the case of self-service. So why do we even need a self-service at all? Then we're going to talk about high-level architecture we had before self-service. So I'll just explain to you where we get started. Then we're going to discuss how we implemented it. So maybe like architecture works through, expect a lot of diagrams, all the funny stuff. And the last would be results and learnings. Yeah. So a bit about myself. I'm Philip. I'm senior software developer engineer at Amazon. I've been with them for 4 years. 3 years I've worked on that platform. So last half a year I was working on internal search things and used large language models to do some fancy stuff. And this month I joined Prime Video in London. So if you want to talk more, I'll be in London too. Happy to meet up. And my background is 3 years of iOS development, which is irrelevant, but have it anyway. I do windsurfing and bouldering, and also my own. I speak about the stuff I build at Amazon, but I do not officially represent Amazon as a company here. Cool. So first part, case of self-service. How many of you have worked as data lakes before? Maybe if you raise your hand, if you work as data lake, as producer or consumer. No? Really, no one. Well, then, what is data platform then? It's a good slide for you then. So imagine you have a large organization. There are multiple teams, and each of the team produce data. And you also have a bunch of data engineers, data scientists, which need to get data somewhere. And there are also a bunch of other teams that want to consume other data that other teams produce in real time, hopefully. And that's the platform that's that's the problem that data platform solves. So it allows you to build a data-driven tech organization where sharing data is easy. It's always easier to find the data set you need. You can get access to it in a standardized way. And you can get access to it in real time. You can get access to it in bulk. Especially the main case we supported was the data engineers, data scientists, which needs to analyze data collected across multiple teams. And this usually happens in large organizations. So my organization we had was, I was working in HR, which is people experience technology. And we had a product which is called data as a service, which was a data platform. And so we supported multiple teams, and that's why we had the data platform. So the customer journey, imagine a problem where you have a Bob, a software engineer that has data in DynamoDB, NoSQL database, and there is Alice, a data analyst who wants to access this data, analyze it, maybe build some data pipelines with Spark, put it in the dashboard and do some reporting on top of that. DynamoDB is not great for analytical queries, so they need to find another storage to put this data somewhere and to be able to query it. Imagine there are multiple Bobs like this, and that's where the platform comes into play. So let's talk about customer journey. So especially the producer onboarding, how data producer would integrate with our platform. So as a first step, Bob would create a ticket to our team. It was all internal. One thing I forgot to mention and explicitly stress is that the platform was focused for internal teams. So all the teams we work with, all our customers were internal teams within Amazon. So Bob created a ticket. Then Tom, an engineer from Pixieda's team, picked up the tickets and they updated the list of data producers and the data sets. It was all stored in code repository. Bob created a pull request with the schema of the dataset. So we as a data platform required our producers to provide us a schema upfront, so we would know, so we could validate the data and ensure the data quality. Bob will create a pull requests with a 3 expert configuration. A 3 expert configuration will tell our platform that this data needs to be exported to S3, which is an object storage. Tom will review all of those configurations and metadata, approve them, and pull it in code repository, and deploy to update the data platform. So data platform would know about the customer. And then we'll grant access to software application of Bob to publish data. And at last, finally, at step 7, Bob will build integrations to CDNs to start sending their events to the data platform. So we're talking about data and metadata. And I think I will need an example here. So this example of the data. The data itself contains a record, which is artificial, generated by ChatGPT. It's not a real record, but basically something that contains, okay, what has happened for employee. Because we worked in HR, our data was mostly employee related. And so in this case, imagine it's like some sort of employee ID, some feedback content. This is a data record. And there is metadata. So example of metadata, which I'll try to color as blue in presentation, would be the list of producers, or like what names of the teams integrate with us, what are their AWS accounts, what is their, who is the owner of the software application, what the name of the software application, and the name of the data sets as well, and the versions, which all needed to have a schema. Schema will be a core part of the data platform, which describes what is the data and what the fields in it. Schema is needed in multiple other ways, but main reason is consumers needs to know what the data is there. And so we use a JSON schema with a specification for schemas, and we stored it also in code. And we talked about the 3 expert configuration. Simplified version of that looks like this. YAML file specifies where you need to have the expert, what are additional transformations you need to do, and what will be the format of the data which will be stored in the object storage. Cool. So imagine, so we talked about producer onboarding, then comes the consumer onboarding as well. A consumer needs to onboard to the data platform to get access to the data, to view the schema. Then it's not all the end. Bob will have to update the schema in the future because the data changes over time. We'll need to investigate the data quality issues and so on and so forth. And all of those multiple changes usually relate to metadata of their, which is stored in code repository. This metadata is deployed through the pipeline, which updates how the platform behaves. And if you think about what problems are with this setup, if eventually you scale, you will see there are bottlenecks. One is Tom, and another one, because Tom needs to support all the customers. And another problem is you might spot is all this metadata is updated through the pipeline. So let's talk about the problems. Time to onboard one customer and its data sets could take up to 2 weeks because first of all, the deployment relies on the pipeline. It's based on the tickets and code reviews that our team needs to pick up, especially if they are in separate time zones, it could be quite lengthy. High operation cost of onboarding, that's another one problem. So for us, we need to spend our time on answering the tickets, making code reviews. And yeah, it becomes a bottleneck if you have to support more than 10 teams. Code repository is also not ideal user experience to view the metadata for non-tech teams or non-tech roles. And to underline it, our platform was basically not scalable to support more teams and more data sets. So what was the solution? I first didn't know about it when I joined this team, but there is a concept of self-service, which basically allows customers to access information, manage it, without involving us as a team who owns the platform. So for us, it would mean that producer consumers can exchange data without involving our team, and the Tom can do something else, build features. So part 2, let's talk about high-level architecture we had before self-service. That's mainly it. So as you see here, we have Pixie Dust in the center of the picture, which had several services. There is ingestion service, which you can probably guess was ingesting the data in real time and in bulk. There is real-time API, which rendered the data in real time. through pub sub subscriptions, through API as well, like REST API. There is data lake, where the data was stored in object storage, and also the bulk export service, which was used for transforming the data, updating its format, and so on. You can probably guess what cloud provider we used in Amazon. And yes, that was AWS. For ingestion service, how it looked like, had the API gateway, which was accepting the events, and there was a Lambda, which we use for compute. And the Lambda, the part which I want to stress here is that use the schemas from the JSON, from their metadata code repository to validate incoming data. Once it's there, it will put the data on the Kinesis stream, which is also known as Kafka outside of Amazon Vault. And we'll use the streams to put the store data in multiple other locations, such as, for example, real-time API and data lake. Another thing is here, you notice that, yeah, code repository was again updated through the pipeline. So that's how Lambda would know there are more schemas and more customers have imported. So that was updated through the pipeline. Cool. Data lake. So data lake would obviously store data, well, not obviously, but it will store data in a S3 bucket, object storage. The data will come there in real time. The data will be stored in JSON. There is a concept of glue data catalog, which is basically a metadata that's required for a bunch of other AWS products to integrate with object storage in S3. So the glue catalog will contain the schema, will contain the location of your data in a S3 bucket. And we used metadata from our code repository to create the tables and glue data catalog to tell services like AWS Athena, which is an engine for querying data on demand with Presto, where the data is located. Data from real-time S3 bucket will be used in multiple other use cases. One of those is bulk export service. And yes, the annoying part, the pipeline, which was used to update the metadata code repository here as well. Bulk export service, another example of the services that we had. Its main goal was to transform, dedupe, and data and put it in another S3 bucket, which had a bunch of Spark jobs. And the serverless way of running Spark jobs is AWS Glue. And Glue Catalog, yes, has a similar name, but does completely different things. We used metadata again here as well to define what jobs needed to run in what sequence. So the 3 export configuration will be used here. And the pipeline again, annoying bit. So part number 3, self-service implementation walkthrough. So just a reminder that we want to build something like this, that our customers can interact, update their onboard as a teams, view the schema, change the schema, set up what features they want to use as Ray expert and so on through their Pixie.js platform, but without us being involved. So what we built is a portal, which is web application that allows customers to do a bunch of use cases. For example, registering their software application would be one of those. Providing the schema, another one. So then to connect their portal with data platform under the hood, we decided to build the backend as well for that, which need to handle all this metadata, so that when a customer adds a schema in the UI, something needs to apply the schema to the platform. So this layer, which will be working with metadata, will be called control plane. And we had more than one control plane because we used microservice architecture, or we migrated to microservice architecture during this time because our team was about to increase in size and we don't want to work on the same code base and want to split the ownership a bit. And at this time, we also believe it will be a much faster way to work on the platform. But we'll come to that point later in the results and learnings. So we split the control planes in multiple one. For each ingestion service, we had ingestion service control plane. For data lake, we had data lake control plane. For bulk export, obviously, bulk export control plane. So let's talk about domain a bit. So there is one concept missing here. So we had ingestion service, which had metadata like limits, what type of mode you're ingesting in, is it in bulk, is it in real time, and the configuration as well, which specified which AWS account the customer was bringing the data from. We had a special domain for real-time API service. We're not going to talk about the details, but yeah, real-time API service had its own domain as well. Bulk export, another piece where was S3 export configurations defined, where there was different transformations that could be applied, for example, specifying the parquet. And all this concept which they have together in common is that they all relate to the core domain, which is producer, consumer, data set, and the schema. And we decided to put all of those concepts, the core ones, which required for the whole platform, in the register service. So on top of all those control planes, we also added a register service. So register service would be responsible for producers, consumers, schemas, schema evolution, which is the process of the change in schema, and ownership metadata. So it would know who owns the data and who are the consumers and how to contact them. The architecture of the register service would be quite simple. It was quite common template for us and many other teams in our organization. Again, API gateway, Lambda, and DynamoDB for storing data. How do we share the data with other control planes? When one thing we considered was, okay, when the producer adds a new data set, let's have register service talk to all the different control planes under the hood and tell them that this data set appeared and now you need to do your own part. For example, the data lake will create a glue table for the data set. Or where the data set is deleted, all the different control planes need to clean up the data. But we decided that's not going to scale because then the register service needs to know all about the different control planes. And we decided to go for choreography pattern here. So we're going to publish the events about metadata changes onto the event bus, and all the different control planes will subscribe to those events and apply changes they think they need under the hood. And register service will know nothing about different control planes. Going to remind you how the data lake service looked before self-service. Remember this annoying pipeline which we used to update the metadata. So now we don't have it. We need to update the metadata in a different way. And imagine the Bobs create support, uses support to create a data set. How do we bring this change to their glue data catalog? Because that's where we need to update the table to create a table. Well, the portal will be connected to register service. Register service will publish an event to the event bus. The data set was created. Now, yeah, needs to be another Lambda that will get this event and apply the change in the glue data catalog. So we decided to put all of those metadata flow, which is used in blue lines here, in the control plane. And data plane was basically everything else, which was handling the actual data. Yeah, that was the separation between the data plane and control plane. Let's talk about bulk export service a little bit, how we changed that. So just remind you, there was this pipeline which updated their code repository and updated the number of jobs that which were running. Now we don't have this pipeline anymore, and we need to update the changes through the portal. So imagine Bob wants to export his data through S3. Bob will go to the portal, configure the S3 export. And now bulk export service itself, because it's not part of the register service domain, will have its own API with Lambda as a choice of compute. And this Lambda will update the glue job, which we're running. So it will create new ones, change them together, or delete them as per Bob's changes in the UI. Well, there is one piece missing. So imagine there is a data set which was deleted, and now all those glue jobs needs to be, or Spark jobs needs to be deleted because their data set is not longer relevant. So we're going to here subscribe to also event bus, which will have the data set deleted events and delete the triggers for the glue jobs which were created previously, if the data set is deleted. That's how the UI looked like. Yeah, you will see here we created a bunch of tabs for different features of our platform. They have the bulk ingestion, you had the schema as well, data quality and data access. We're going to talk a bit sooner. The export bit will go into the export tab. That's how the schema looked like. So we have basically a table with the name of the properties, the type, the lengths and other requirements, and the descriptions which customers could view. Results and learning, the last bit. So the benefits of self-service portal, or self-service feature, or the process itself, because it required more than just a portal, was, yeah, we launched it, we onboarded multiple teams and hundreds of data sets pretty easily. Because, yeah, we decreased on board the operations cost for sure. We catalog accessible in the portal and not the code, also simplified customer interaction with data platform. We have seen how multiple non-tech customers came to the platform, use the links in their conversations, and they could now, yeah, talk about the data or like the metadata of like what the data set is and what are the fields in there, much easier than it was before when it was so sorted in somewhere code repository. Portal also allowed us to bring more UI features, such as access metrics and data quality metrics. And again, expand them not just for some developers, but to the whole organization and show them to everybody, yes. A side effect, an interesting side effect. So we had control planes and they had their own APIs, and which allowed us to expose them to software engineers for better development experience. So that allowed us for, in future, as a potential idea to integrate a bunch of internal tooling such as AWS CDK, which you can use for defining your infrastructure, and create the data set for your software application, which will be exported to our platform together with all the infrastructure code. And yeah, so that will be a better, even better experiences for software engineers who want usually to define all their infrastructure and code to be easily replicated across regions or stages. And yeah, having APIs could easily allow us to solve this use case as well. And we definitely saw how teams can now create data sets in minutes and build data integration in days. So side effects of event-driven architecture. So remember, we started using event bus for sharing events about data sets and producers and all other metadata configuration changes. So that allowed us to simply build audit service that could store all the different events and show past user actions in the UI, the history of changes. Because event bridge was already there, we just need to plug it in and store in some sort of open source cluster, and then later display on the UI. Which is, we come into another good point. So event bridge, we use event bridge as a service, AWS service to share the events, and has an interesting feature, which is archive, which is basically stores under the hood all the events that you previously sent to it. And the reason this feature allowed us to delay investment into a drive backfill infrastructure, which solved this use case of audit service. So we built audit service half a year later than we launched. But because how would we know all the different history that happened before? Well, we could replace it with event bridge. And so solving the use case like that was really easily with event bridge archive. Speaking about lessons learned, so we unexpectedly had high costs in self-service implementation. So even though their architecture seems technically simple, what you have to do is, yeah, the domain itself wasn't also overly complex. We know we had years of experience of running the platform, even though it took us a bunch of time to set up a bunch of different control planes, get it right, get the schema right, and even if you could parallelize it across multiple teams, about multiple engineers with a microservice architecture, where each of those control planes had its own pipeline and its own code base, our team didn't grow as fast as we expected, and so it's a bit unsure if the move to a microservice architecture was a bit premature. And hard to relate it because it's hard to collect all the data, like redo the same architecture without microservice move. But we definitely noticed there is a cost to splitting your servers into multiple ones and having to set up the same thing all over again, even if you can automate it or copy it a part of that. Also, after our release, a year later, there was a new AWS service that popped in, which is called Data Zone. Data Zone allows you to discover and share Glue catalog, which is the metadata, across organization with a built-in application. So basically allows you to have this catalog of the data quite easily and potentially could be one of the solutions we could consider. But I put here as a note that first of all, yeah, there is a service that exists that help you to your organization to share the data with everybody across multiple teams with a beautiful UI. But also we might have considered simpler options than investing into self-service and building this whole architecture. That's it. So thank you so much for your attention. Thank you, Justit, for hosting and Cloud Native as well. You'll find my socials. There is a QR code with all the social links as well. And there is a YouTube talk about this, a bit more detailed if you want to watch it later on, which is also on this QR code. That's it. Do you have time for questions? Yeah, we do. Cool. Then, yeah. If you have any questions, let me know. Yeah, there's one over there. Sorry, can you speak up out loud a bit?
Yeah, sorry.
Yes. So basically, I think if I have used it just for a quick while and explored a little bit, but if I understood it correctly, you just plug it in. You already have your Glue catalog. So basically all the tables defined with the schemas, then just register it and with a couple of clicks in data zone. I think you do some quick steps to set up and then that's it. You have the application up and running. And I think you can then use this application to browse the data. And yeah, so you don't need to manage anything. Serverless completely, yeah. Yes, with less effort, yes. Yes, there is one.
Sorry, you told one of the main benefits of building self-service is to let non-technical person to could be tenant. Right? I'm just curious how non-technical person could provide you something.
Yeah, that's a good point. We also, for that reason, we also built a bunch of other tools that allow to integrate with other internal data platform teams solutions we had within Amazon that will discover this JSON schema and put it in the portal. So yeah, I didn't talk about part of that, but part of the things we then later encountered this pain point and we built solutions like some automations to populate this data schema from scratch. Yeah.
And one more question.
Yeah, go ahead.
Sorry, you told that you were using event-based
Event bridge
system, event bridge based on Kafka, right? For right? And as far as I know, Kafka has pretty limited size of the message. So I'm wondering if you are using this for data pipeline as well, or just for events.
Yeah.
Or if it's just only for events, what would you use it for data itself?
So yeah, good question. So we used event bridge bus. So the event bridge is a service in AWS, which is serverless event bus. For sharing metadata, the limit for the payload there is 256 kilobytes. And because our metadata never actually grew that large, it was fine for us. For sharing the data, actual records, I think Kinesis, not sure about Kafka, has a 1 megabyte limit. And in the nature of our domain, we never had like large enough records that wouldn't fit the 1 megabyte record. So there is a workaround. I think the usual workaround is you put this, on Kinesis or Kafka a pointer on S3, and they actually store the data in S3, and then the subscriber with Kafka will need to pull the data from S3. So we had a workaround for that if you ever needed, but we never actually crossed the limit of 1 megabyte. Yeah. Any more questions? Looks like no. Thank you so much. I'll be out there somewhere. Yeah.
Could you check the Zoom?
Can't show exactly. Select the other.
But see,
Yeah, you're screen sharing this right now.
now I select the entire one. Entire screen.
This entire screen is what you're showing right now.
No,
As long as you put the presentation on that screen.
you can check it right now. If it's fine, let me see. Yes.
Yep, you're fine.
All right. Welcome again to Cloud Native London. My name is Saeid, and I'm working as Kubernetes Architect Director in CBRE, as well as I'm founder of Kubedemy.io. You can find, if you're looking for any kind of Kubernetes tutorial, you can search for Kubedemy, and you can learn more about Kubernetes. Our agenda today is to know how Kubernetes platforms are built, with a real example and a real journey about how companies start adopting their infrastructure with deploying Kubernetes, and then building an enterprise-grade platform with Kubernetes. But in our diagrams, I use the same one to explain, and I use them to teach enthusiasts about the Kubernetes platform consistency, security, compliance, add-ons management, cluster management, because then you can see the diagrams are completely show you how the platform about the Kubernetes should be fit in the company and how other teams engage with your platform. But today, we go to the journey of Kubernetes adoption in companies, how different teams engage with the Kubernetes team, and then with your Kubernetes environment. And after that, how company decide, okay, it's time to build the Kubernetes platform. Before we start, scan the Kubedemy thing. Scan it. Nice. We should scan it first. Okay. Let me do something. Okay. How many clusters and nodes do we have? Could you guess in a CBI? We are enterprise grade company, and we have our Kubernetes platform. Can you guess how many clusters we have right now? 500, 350. Okay. Right now we have more than 600 clusters, 30,000 nodes, 30,000 worker nodes at scale. And today I will tell you how we built our platform, and you can use the same approach, and you can find, okay, how and why we went through that journey to build our platform at scale. The first question, how do companies move from an environment to platform? What is the difference between the environment, Kubernetes environment, and then how they can adopt and move to creating a platform? So let's deep dive into the Kubernetes growing journey with DevOps, Cloud, Kubernetes Platform, and all-in-one pattern. The phase one, when you want to deploy a Kubernetes in your environment, is to have a development team. You have one development team. As a startup company, you start with a development team, and you have a DevOps team, a small DevOps team, and your development team, with help of DevOps team, they built a new infrastructure. They deploy a couple of clusters, at least one production cluster, a couple of lower environments for test, for dev, for non-prod environments. And in that case, the journey starts. And you have one team, a couple of clusters, one environment, and in that environment, development team and DevOps team make the final decision to, okay, what version of Kubernetes we need, what tools and add-ons we need, which versions, which tools, which operators should be installed inside the clusters, and the small team of the DevOps will manage the clusters in a hassle-free, really easy manner. Because there is no any other clusters, there is no any other tools, any other team, and one team, one DevOps team, and one environment. It's easy to manage. Then, after a while, your company grows. You have two development teams right now, and they have their own requirements. Development team, two wants to deploy, for example, Ambassador as an ingress controller, because Ambassador provides some sort of tools. They need to deploy their application to make it books. And after that, as a DevOps team, you don't know, you are going through a big storm, because your environment right now trying to make it bigger and bigger. And the thing is, now your environment gets bigger than before. More application, more needs, different requirements. DevOps team is not responsible for managing everything in that environment. And you need to pay more because you need different tools. And different tools means more consumption, more resource in that environment. In that case, challenge can be solved. It's not easy, but acceptable, because you have a small DevOps team, two different environments with two different type of tools and technologies. And in that case, no one is aware of the upcoming storm, because your platform gets bigger and bigger and bigger. And then your platform, your environment will be something like that. You have a couple of new teams, and they have their own needs. I want this, I want that. Please deploy this application. Please deploy that application. We need this operator. No, this version doesn't work. We need some different configuration. No, this configuration with ingress engineering doesn't work with our application, and we need other and different sorts of tools. In that way, you face with something new. More teams, more clusters, more requirements, more everything. Everything will be different. And DevOps team says, okay, we need more resources, human resources. And the leaders in your company say, okay, hire more DevOps engineers because we need to assign some more tasks to more DevOps engineers to achieve our goals. And then in phase 4, you have the big DevOps team. They try to solve the issue, and after that, you face with a new issue. Big team, big challenge, big drifts. And DevOps team ask themselves, okay, who did this change? Who did that? From where? With the command line? From which tools? With Terraform? With GitOps? With what? And there is no any standard flow in your team in that case. And because you have a big team, you will make big mistakes. And your environment and your team is really hard to manage. And leaders say, okay, growing the team was a bad decision, was a wrong decision. Let's create a small things. And then your platform will be something like that. You have a different development team with a different DevOps teams. They are responsible to manage their environments, just like you can see. And what happened in next, the phase 5 will begin. The small separate team, the small silos, which means different ways of solving the problem, different tooling, different of everything. In a phase 4, you had one team and n challenge in your environment. But right now, you have n challenge in your environment. And what happened? All the DevOps teams spend more than 70% of the time on the same tasks. To deploy a cluster, to upgrade the clusters, to adopt the applications, add-ons, tools, and etc. And it's a waste of resources. And the leaders in that point said, we need a new way to solve our problem because growing the team didn't work in the environment, in the company. Making separate teams, small silos didn't work. And now it's time to build a Kubernetes platform. Your environment will be something like that. You need to create a Kubernetes platform team, and this platform team is the team responsible for creating the templates, add-ons, landing zone, deployment tools, and all the things. And in that case, if someone needs an environment, someone needs a cluster, they have to ask the Kubernetes platform team. We need these tools. We need this Kubernetes version. Provide us something. And what happened in that case? Your Kubernetes platform team will create a couple of blueprints. Blueprint 1 is a blueprint with a sort of applications. Blueprint 2 for other team. Blueprint 3 and etc. And they deploy them to the separate clusters. What happened in what is the issue with this approach? Right now, we have a Kubernetes team, we have a Kubernetes platform team, we have a platform, we have a couple of standard blueprints designed for our customers, for our consumers, and we have many clusters. What is the issue? Mm-hmm. Yeah. Other. Yeah. We have many issues right now. The first issue is, imagine we have 3 different teams and they want the same blueprint. In that case, we have to create a couple of clusters. It means we have to spend more cost on the control plane of the cluster to achieve the same thing. And what happened next? Someday, our stakeholder of the company, security, business team, and other stakeholders come to the picture and they say, we need more insights. Because right now we have more resources, we have more applications, we have dozens of clusters, and they need security, compliance, cost management, monitoring, logging in the unified platform because they want to know what's going on in the platform. There is our weak point that right now we spend lots of money without achieving something special. And what happened next? They provide you something that they want to deploy into the all clusters. For example, the security team tell you, we want to deploy telco for runtime security. We want to deploy OPA as a policy engine. The business team says we need open cost for cost management. We need Prometheus. We need anything to check the cluster and check what's going on in the platform. And the Kubernetes platform team needs to add these tools, these operators, in their blueprint. And the issue is, when you have a couple of different blueprints, keep these sort of tools in sync is really hard problem because someone needs to take care of all of them. It's just two blueprints right now. But in reality, when you have much more teams, much more blueprints, someone should take care of, okay, I have to update the blueprint 1, blueprint 2, blueprint 3, and all of them. And the Kubernetes platform team decide to do something else. Create the base blueprint, and based on the base blueprint, you create the other blueprints, the child blueprints, and add these things. But again, the cost of the cluster makes you unhappy, and the business team will be unhappy that you spend lots of money on something that do not provide you something special. You can solve it by something different. And in that case, your Kubernetes platform team will do something else. You create a new layer for R&D, creating POC, write to links, and solutioning, and check, okay, what really our development team and other teams need inside the Kubernetes platform. And in that case, instead of blueprint 1, blueprint 2, blueprint blah, blah, you have one standard blueprint and tell the users if you want to deploy your application into the platform, you should use the standard blueprint. This is the standard blueprint we provide to all the teams, and we have some exceptions. For some teams that they need to adopt their applications, or their application is a legacy, and it's something like a brownfield application, and we have some exceptions. But 90% of your clusters, your consumers, will go to the one or a couple of Kubernetes clusters. And in that case, you will face the new issue. Shared multi-tenancy model, sharing the resources to the user, creating the chargebacks, how you should charge the team. Okay, you use this cluster 20%, now you should pay the chargeback, or something like that. It's a new issue. And after that, your company will be growing. What happened? Leaders tell you, we need to go and adopt our platform in a multi-cloud way, instead of deploying the clusters and anything in just, for example, AWS, we want to deploy multiple clusters in other cloud provider as well. And right now, your Kubernetes platform should be deployed and adopted with a couple of cloud providers. And what happened? You need two new teams. Cloud engineering team, network team. The cloud engineering team here should deploy the infrastructures, need to deploy your clusters. For example, you need VPC, and in that case, Kubernetes platform team is not the team responsible who is responsible for deploying the VPC, or the Kubernetes team is not responsible for creating IAM roles, policies, and etc. And the cloud engineering team should do that. For assigning the IP address, for IP management, and for connecting AWS cloud, your AWS account to your Azure account, VNet to VPC, the network team should chase it, and you need more teams. And after that, you need new base blueprints, EKS-based blueprints, AKS-based blueprints, GK-based blueprints, and then based on any of them, you should create a standard blueprint, and then deploy all of them to clusters. After a while, you face with a new challenge. Your company will be grown, and you need to deploy your application in Edge. You need IoT Edge team. And in that case, IoT team is the team should work with cloud team, network team, Kubernetes team to create the base blueprint for the edge, because the architecture is different. Right now it's ARC. It's not Intel, it's not any other type of normal architecture you run in a cloud provider or on your laptop. It's completely different. You need something like Kubernetes to run your application at the edge, to find the issue at the edge. And in that case, you need to expand your team, to invest more money. And after that, you need some sort of communication, connection between your edge devices, your main devices, edge clusters to main clusters, and that's it. Base 12. We are still working on it. This is what I try to talk about that. Give a sec. If you want to learn more and get the animated version of these diagrams, you can go to the Kubedemy. And if you want or looking for learning AWS EKS with the black belt course, right now it's free. You can register for free on kubedemy.io. And now it's time for questions. The time? It depends. If your company, just like CBI, I'm working on that, we went to phase 11 in 2 years. But in some companies, maybe less, maybe more. But from a start point, in 2 years, we went to phase 11. And we don't know what happened in phase 12. Any other question?
From the expected yourself for David, about how things are going. Are we going to come to the next slide?
No, it's done. Because this talk, I removed a couple of slides because I just had 30 minutes and it's not time to go deep to, okay, we have right now our platform. What is the security issues? What is the storage issues? What is the challenges about the networking? what is challenge about, for example, deployment of WAF, multi-tenancy. Every day we face with new issues, but in the next meetup, it may be in Kubernetes London or Cloud Native London. I will continue this slides to tell you about something more based on these slides I'm telling right now.
So one slide is where you are now, right?
Yes, right now the phase 12 is where right now we are in and still work on it. Okay, what is the next step?
What is edge environment?
Edge environment, let me explain what we are doing now. We have dozens of clusters in AWS, in in Azure, in GCP, and this is our main clusters. We have some sort of tools and technologies, for example, Raspberry Pis, NanoPis, Tinkerboards, Asus Tinkerboards, and a couple of other boards that we deployed K3s. K3s is a Kubernetes distribution. You can deploy them on ARM technology, on ARM CPUs. And we deployed K3s into our boards, and then they connected to some physical equipment, for example, for temperature, for some security scanning, or a couple of them. And when our customers, our team is a Kubernetes platform team, and our customers is company development teams. When our customers wants to deploy something, for example, they change some line of code in a temperature application, they want to deploy it into multiple environments, because right now we are a company managing infrastructure and data center of Amazon, Azure, and Google Cloud physically. We manage their data center physically. And in the case of security, temperature, cooling, electricity, anything related to their environment, we are responsible to manage it. And for example, when our development team changed something, we deployed first to our main clusters at the cloud, because the controller will be deployed to the cloud. And our edge application deployed to our edge devices that connected directly to, for example, temperature sensor. And then get the information, send it back to the controller decide, sending some others, or do anything they have to do. Any other question?
Yes. That's right. What your footprint consists? What is footprint? What kind of right you bring it on? I mean, some ground complaint or.
So the blueprint is a set of tools. For example, in case of Kubernetes networking, you need something to deploy to your Kubernetes to get network started and assign IP addresses to your pods. Or for example, you need to have some secret store to manage your credentials, secrets, certificates. And in the case of blueprints, we create a set of tools and name, okay, this is the standard blueprint. And when someone in a Kubernetes platform team wants to deploy a cluster, they should decide, okay, if the application, we have some request form, when the user creates a request for a cluster or for environments, we call them project. Because in our system, there is no any cluster. It's completely abstract like. They open the request form. In the request form, they have a couple of questions. Okay, your application can deploy in such an environment or no. Okay, and after all of them, they select our application needs to deploy into this region, into that region, and based on the request form, we're creating some templates. We have some ready-to-go templates with a cookie cutter, we create a Terraform code, automatically deploy it, and then the project that we call landing zone, they're able to use it. And then they can deploy their application. They can see the clusters directly. When they want to deploy something, we have the federation in place, and then they create, for example, federation deployment based on the request, it deploy automatically to a couple of clusters.
Some kind of pipeline which can
Yes.
perform, which deploys based on, and
Mhm.
then you have bunch of counter deploy on the point.
Yes, we have ServiceNow. In ServiceNow, they created the ticket, they create a request. We have some ready-to-go templates. We read the ServiceNow ticket, create a template, and generate their project, their landing zone code, apply them with the Terraform, and after that, the service is ready for them. They can start it.
And on which level of opportunity compared to the previous speaker? I mean, is it still someone who is manually handles this service
No, it's
now request?
completely, yes, it's completely automated.
Or is it-
Yes. No one do. We don't know how they use the platform or when they create a request ticket. ServiceNow automatically read by our tools, automatically generated by Kubernetes, send it back to the pipeline. The pipeline will be started, automatically deploy the landing zone, and then user can use it.
Thank you.
But so your use case is a little bit more special, I think,
Mm-hmm.
because when I was doing Kubernetes, where is your governance in all this? So your use case is you actually have servicing many different that they can choose. And I'm thinking more into well, it's a single company or a project you have to run. And that's where usually you should have governance.
Mm-hmm.
A little bit more to avoid proliferation. So,
Yeah.
tax rates you have to bring up.
Yeah, exactly. Normally, if your company has some small sort of application, you will be here. It's something like that.
Well, or even more before.
Yes, or maybe one before. Just one team, one DevOps team, and a couple of clusters.
No, many DevOps teams,
Mm-hmm.
but not a choice.
Yeah.
Say governance.
Yes, yes. So it's something different because the use case may be different.
Yeah.
Mhm. And in some companies, mostly in enterprise companies, they have lots of brownfield applications that no one wants to change it. For example, they wrote some application, use some SDKs, and no one wants to change it. For example, if a couple of years ago, they had some tracing application, no one wants to change the code to use OpenTelemetry, to adopt it with the new tools, and no one can enforce it. No one can enforce development teams because every day their job is to add some new features. They don't get back to the last position or the last task and change something they already developed. It's really hard in enterprise.
I know how you sound like, but if they do that in where I work, then the whole thing is deleted. Automatically.
Yeah, but I think it's completely different at the enterprise grade.
Yeah.
Any other question?
For your case here, inside cluster, what will be the Kubernetes team, platform team, cluster, like how many members?
50, right now we have 50.
And they had something, know everything over.
Just where? Yeah, just everything related to Kubernetes. Yes, and for the other things, we have separate teams. Cloud engineering team is a separate team, networking is a separate team, IoT team is a separate. And Kubernetes platform is a team just focus on everything inside the cluster, everything related to Kubernetes. not at the infrastructure level, network level, or kilo level. We have all of them. Most of all major providers, EKS, DKE, AKS, on Ali Cloud, Digital Ocean Kubernetes, as well as on-premises. So on-premises, from our perspective, is a Kubernetes cluster deployed as a self-managed. Doesn't matter if it's on-premises in a real data center or in EC2 instance. Yeah.
Can you foresee already the next solutions happen like at the edge last month?
I think, based on what I knew from our company, the next level is to adopt Kubernetes with serverless, with something like kubeless or some other kind of tools. This is the next generation company may want to go.
Do you have a maximum unit size? I mean, I know you're talking about some of the standards, but at the end of the day, they actually need to use their own images to run their own. So, you have a maximum unit size.
Yes.
What is the ideal size, or what's that word?
So, it's other topic, but to get you familiar with that, 1 megabyte of image in the enterprise grade level can create a big latency in downloading the image. Because, for example, we had the same issue, and because when you have a one cluster and you have a couple of microservices, doesn't matter how much the size of image. It doesn't matter. 1 gigabyte, 2 gigabyte, because the Kubernetes cluster wants to download and pull it one time. But when it goes to enterprise grade, then you have 30,000 nodes, and you want to download, for example, 1 megabyte, which means 30,000 nodes needs to pull the image of 1 megabyte. And you can imagine what will happen. The cost in a network side, the latency to download and pulling the image and deploying, and mostly we had an issue at the edge, because at the edge, the internet in some countries is not good. In some data centers, we have some latency, more latency than other data centers or cloud providers, and the size of it is really important. And how we manage it with some tools and controllers JFrog provides. Yeah. You all sorted, yeah? Okay. Thank you all.
How much do you get involved in teams who have brownfield applications and are transitioning to try and run your stuff?
Yeah. So it's not part of our team, because our platform team, our Kubernetes platform team, the goal of our team is to provide and deliver platform. In our company, we have a couple of contractors, and the contractors is working, all of them working in a team. We call them migrating, and they are responsible to decom the old clusters, create a new project landing zone, and help development team to migrate their application to Kubernetes platform. But if they need something from our team, or if they face with some issues, for example, they want to change some configuration in ingress controller, in other operators, then we help them to get it sorted.
That's okay. Do you force version of Kubernetes?
No.
Do you still have all the shit?
Yes. Yes.
Okay.
In our platform, we don't have. But before creating the Kubernetes platform, because we went to this phase, to phase 6, we had a couple of clusters, thousands of clusters, with different versions. And right now, the main goal is to migrate these clusters to the new clusters, to the new platform, and become one of them. But the issue is, for example, some teams use Argo CD or Argo events with it, in old versions that can be deployed, for example, to Kubernetes 1.18. And if we want to deploy the application and the resources to the new clusters with a new version of Argo events, Argo workflows, Argo CD, the manifest is completely different. The application is deprecated, and right now they have to change something in their manifest, or maybe in their code, or maybe in the flow of the events, the workflows, and it's really a big challenge. But right now, in our team, we have.
Just one question. Do you think cloud providers will provide this as a managed service? Because I know EKS as a EKS blueprint.
EKS blueprint is a Terraform. It's just a Terraform code. Then you deploy EKS with, you want to deploy EKS with Terraform, you can use their module, the EKS module, Terraform module, to deploy the cluster and use the EKS blueprint to deploy a couple of add-ons they added. In our company, we have something like the EKS blueprint with the Terraform, but we manage it and we wrote it. It's completely fitted to our use case. Right? Thank you. Okay.